Hi everyone, today I would like to talk about Cholesky factorization. In the previous video I talked about the QR factorization, which is a very important factorization used a lot in solving system of linear equation, least square estimation. It has many different algorithms proposed for that, like Gram-Schmidt, Householder method, Gibbons technique, right? Cholesky is another very well-known factorization that today we want to talk about that. Before talking about Cholesky factorization, it's very important to know what is positive definite matrix, right? Because the requirement to apply Cholesky factorization to a matrix is that the matrix should be positive definite. Okay, so let's start. Positive definite matrices, or in short, we usually show them by PD, are square and symmetric matrices. Remember, there are two requirements. Matrix A should be square, means the same number of columns and number of rows, and it must be symmetric. So in case of real matrices, symmetric means that A transpose is equal to A. Okay. Then a matrix is said to be positive definite if X transpose AX is greater than 0 for all vector X that is not equal to 0. Right. So this quantity is sometimes denoted as a quadratic term. Quadratic term should be positive for all X that is not equal to 0. Another way to prove this one is this. Says that X transpose AX is greater than or equal to 0, and the 0 only happens, meaning that X transpose AX is equal to 0 if and only if X is equal to 0. So think of it like that. X transpose AX is always greater than 0 for any vector non-zero X, right? And 0 only happens when X is equal to 0. So that's the definition of positive definite, very important. We have another broader class, which is called positive semi-definite, which in that case, X transpose AX is greater than or equal to 0 for any X. So X doesn't have to be 0, but still X transpose AX might be equal to 0. So positive definite, in a sense, is a more strict version of positive semi-definite. Okay, now let's take a look at the properties. These are very important properties. One, all the diagonal elements of positive definite matrix are all positive, right? Why is that? So we write the definition. X transpose X should be greater than 0. And it's equal to 0 if and only if X is equal to 0. Right? So now X transpose X is greater than 0. This X can be any vector, any non-zero vector, right? So let X to be a standard basis vector, right? What do I mean by that? That's X to be EI. What is EI? Is nothing but zeros everywhere except 1 in the ith location, right? So for example, like E1 is this 1 0 0 0. E2 is what? 0 1 0 0 0, right? So if you let X to be EI, then EI transpose AEI is equal to AII. Element on a main diagonal correspond to the ith row and ith column. But wait, X transpose AX is greater than 0 if X wants to be positive definite, right? So this element should be greater than 0. Therefore, it is still necessary condition. Remember, if a matrix is a positive definite, then elements on the main diagonal are all positive. That's what it means to be necessary. But if all elements on a main diagonal are positive, it doesn't mean that the matrix is positive definite, right? So it's not a sufficient condition. For example, consider A to be this 1, 2, 3, 5. This is not a positive definite matrix, but all the elements on a main diagonal are positive, right? So if all the elements are positive, it doesn't mean that a matrix is positive definite. Correct. Now, the diagonal elements of positive semi-definite matrices are all non-negative. When I say non-negative, it means that the diagonal elements can be 0 as well, right? Very good. So for positive definite, all the diagonal elements are all positive. For positive semi-definite, all the diagonal elements are non-negative, so they can be 0 as well. That's very important property. Let's go to the second one, which is extremely important, and it's a fundamental of Cholesky factorization. This is called short complement. If a matrix A is positive definite, right? You know it's symmetric and is a square, then A can be partitioned as follows. So you can only A11, this is a scalar, This is a notation, right? A2 to N, 1 means that the first column and the row 2 all the way to row N, right? And this one means the second row all the way to nth row, and the second column all the way to nth row. This one, you can write it like this as well. The first row and the second column all the way to the nth column. For notational purpose, sometimes you see in the literature they write it like that to tell you that, hey, this element and this element are transpose of each other. Let's take a look at an example. If A is this, 1, 2, 3, 2, 3, 4, 5, 6, 7. Sorry, it should be 5. It should be positive. It should be symmetric, right? So then A can be partitioned like this. This can be A11. This can be A1, 2 to N. This is A2 to N. Here is N is 3, for example. 1, and this is A2 to N, 2 to N, right? Okay, so if you look at this one, for example, you see that A2 to N, 1 is nothing but 2, 3, right? And A1, 2 to N is nothing but 2, 3. So they are the same thing, it's just transpose of each other. Sometimes you see in notation, they write it like this, right? Also, you can write it like this as well, it's perfectly fine. Okay, so that's for the notation. Now, the matrix S, which is called the short complement of matrix A, S for the short, right, is defined as A2 to N, comma 2 to N, this one, minus 1 over A11. Remember, A11 is scalar, so you can write 1 over that. But remember, we assume A is positive definite matrix. Therefore, element on the main diagonal, they are all positive. So this one is positive, right? So A11 times A2 to N, A2 to N, times, you can call it times A1 to N, times this one, right? This is all called the short complement of matrix A, right? And here I said that, remember, A11 is not 0. It's also positive definite. So if A matrix A is positive definite, then its short complement also is positive definite. This is very important. This is fundamental of Cholesky factorization. We start with the Cholesky factorization order n, and we simplify that to Cholesky factorization order n minus 1. And this is how the numerical software like MATLAB, Python calculate the Cholesky factorization of a matrix. Okay. Now let's go to the next property, invertibility. If a matrix A is positive definite, then it's invertible, right? Why is that? If you want to see if matrix is invertible or not, always, as we have seen in the past, you write AX equal to 0. Then you need to prove that if AX equal to 0, then X equal to 0 is the only solution. Go ahead and multiply by X transpose from the left side. What you get is X transpose AX equal to 0. But wait, I said A is positive definite matrix. Therefore, X transpose AX is 0 if and only if X is equal to 0. So we prove that AX equal to 0 give us X equal to 0. Therefore, A is invertible. Very important, right? Now, this is like this. If A is positive definite, then it's invertible. So it's a necessary condition. It's necessary condition, right? If it's a positive definite, it's necessary to be invertible. But if a matrix is invertible, it doesn't mean that this is a positive definite, right? So for example, if you consider matrix, right, we'll get to this property that has a negative eigenvalues, right? If a matrix has a negative eigenvalue, it still is invertible, right? But it's not positive definite, right? Because we get to the properties, these properties, that eigenvalues of a positive definite matrix, all of them are positive. The matrix is not invertible if it has a 0 eigenvalue, right? Remember? So it can have a negative eigenvalue and still be invertible. But if it has a negative eigenvalue, then it's not positive definite. Okay? So remember, this is only a necessary condition. The next one, eigenvalues are all positive. Yes, eigenvalues of positive definite matrix are all positive. This is very important. Now the next one is more important and contains this property, is this one. Determinant of positive definite matrix is always positive. Well, what is the determinant of a matrix? It's defined as a product of eigenvalues, right? But if each eigenvalue is positive, then the product also is positive, right? Positive, non-negative, not non-negative, but positive, right? So these properties can all be related to each other. This property, this one, and this one, right? So if the determinant is positive, if all eigenvalues are positive, the determinant is positive. If the determinant is positive, this means that it's not zero. So matrix is invertible. You can also relate it to this property if you think about that, right? The diagonal elements, for example, you can come up with a matrix A to be this, a diag. 1, 2, 3, right? Like this one. This is matrix A. 1, 0, 0, 0, 2, 0, 0, 0, 3. What's the determinant of this matrix? Is a product of elements on a main diagonal, right? So determinant of A here is 6, right? Therefore, determinant is positive. Here, eigenvalues are positive, right? And all elements on a main diagonal are positive. So that's just one way to check all these properties. But these are very important properties, okay? But it's not like you can conclude one property from the other. Because, for example, if you consider, if I make this one like this, -2, -3, it's still the product of the elements are positive, right? But this is not a positive definite matrix. So it's very important to know that these are not a sufficient condition. These are like necessary condition. If a matrix is positive definite, then it has all positive eigenvalues, right? So very important to consider how to actually interpret these properties. Very good. Let's talk about the gram matrices. I claim all gram matrices are positive semi-definite. What was the definition of gram matrix? B transpose B is a gram matrix, right? So let's take a look at that. We apply the definition, X transpose BX, right? So this is like our A matrix here. Now we are all expert. You can write this one as a BX transpose times BX. This is equal to BX normal BX squared, right? In general, this is greater than or equal to 0, right? Because this is equal to 0 if BX is equal to 0. So in general, this is greater than or equal to 0. So gram matrix, what in general is a positive semi-definite, right? Well, now let's see under what case this is a positive definite. It's a positive definite if this quantity here is equal to 0 if X is equal to 0. So we want norm of Bx squared equal to 0 give us X equal to 0. This means that Bx equal to 0 give us X equal to 0. This is only possible if B has a linearly independent column. That's very important. Therefore, B transpose B is positive definite if and only if B has linearly independent columns. Otherwise, B transpose B is always positive semi-definite. Okay, that's very important thing to consider. Now let's talk about the Cholesky factorization now. So we claim every positive definite matrix A can be written in this form. A equal to R transpose R, where R is an upper triangular matrix, where the elements on a main diagonal are all positive. That's what this statement says, right? So in a sense, you can translate R or interpret R to be a square root of positive definite matrix A. So for example, if this A was a scalar, 1, 1, 1 matrix, R was a square root of A, right? And if A is a matrix, you can consider R to be a square root of, you can interpret that, visualize it like that, right? So we get to how to calculate this matrix R. But before that, let's just motivate this. If this A, again, remind you, can be partitioned like this. 1, 2 to n, 2 to n, 1, and A2 to n, 2 to n, right? In a sense, you can write this one as R transpose R. Where R, this one is R11, this one is R1, 2 to n, 0, remember, upper triangular. R2 to n, 2 to n. And this part is going to be a transpose of this. So it's going to become R11, R1, 2 to n transpose 0 or 2 to n 2 to n, right? So that's what this one says. We get to see how to calculate the Cholesky factorization of matrix, right? So before that, let's see how to solve a system of linear equation using Cholesky factorization. We want to start ax equal to b and solve for x. Very important caveat is a should be positive definite. So go ahead and write the equivalent of a. Now that we know it's positive definite, a is going to be r transpose r, okay? So we want to solve this equation. First, let rx, this term, is equal to w, right? In that case, we are going to solve r times w equal to b. But this is very easy to solve for w because r itself is an upper triangular matrix. Therefore, R transpose is a lower triangular matrix. So it's a very easy problem to solve, right? It can actually be easily solved because it doesn't, you can easily solve using back substitution and forward substitution, right? Okay. Now, once you solve this one, you get a W from this. But then we had Rx equal to W, right? So from here, you calculate W. So then you have Rx equal to W. You have R, you have W, and this one also can be easily solved because R is a upper triangular matrix. Then you can find the X. So that's how we find the solution of system of linear equation using Cholesky factorization, given A is positive definite. Otherwise, A wouldn't even have a Cholesky factorization. Okay. Now let's see how to compute the Cholesky factorization of a matrix. Again, given positive definite matrix A, we can partition A like this, right? We can partition A like this, what I showed before multiple times. Then R, as I showed before, like here, can be written like that. This is R, right? Then you can actually find the R in terms of A. So R11, this is also on a scalar, is equal to a square root of A11, right? Okay, so it's very important element on the main diagonal to be positive. Now you see that. If it's not positive, then this one really doesn't make sense. Okay, so it's going to be a square root of A11. Now, R121, the first row, and the columns 2 to n is equal to A1 2 to n divided by R11. Right, so that also can be easily calculated. Right. So what we have here now is we know that this element also is 0. So we calculate the first row without any problem, right? But now we need to calculate this one. Remember I talked about the short complement? This one, this element, this one, this R 2 to n, is a short complement of, is calculating short complement of A, right? This is nothing but A 2 to n minus 1 over A11, exactly the short complement. A2 to n 1 multiplied by A1 to n. This is short complement of A. Right, and that's what this expression here says. Right, you see, this is using the notation that I introduced before, but you can also write it like this. Right, very good. Now wait. So we get this R2 to n, right? And we go ahead and apply the Cholesky factorization iteratively on this. Why? Because the short complement is always positive definite. So this R 2 to n will be our new matrix A, which we calculate the Cholesky factorization of it, right? So as I said here, then keep doing this until we get a 1 by 1 matrix, until this become 1 by 1, right? So in a sense, we actually reduce the Cholesky factorization order n to Cholesky factorization order n minus 1. Right? So it's very important. If A is positive definite, then the short complement is positive definite. Otherwise, we cannot really apply the Cholesky factorization, or you cannot really calculate this short complement. we cannot really do the Cholesky factorization of this short component because it wouldn't be a positive definite matrix. Okay, so that's it for the Cholesky factorization. In the next video, I'm going to talk about the nonlinear least square and nonlinear least square for the convex function. Okay, thank you so much for listening.